Hi, and welcome to our second video on arrays for the data structures course. I'm going to share my screen and we'll walk through some fancier sorts of arrays that you may find useful as you go along in data structures. I'm calling these fancy arrays. That's not an official term, of course, just as a vanilla array was not. But these are probably better called improved arrays or extensible arrays because they offer some of the same behavior and performance of the simple array, but they add a lot of extra features. So just to recap briefly the previous video on plain ordinary arrays. In that video, I called them plain vanilla arrays, but we went over some of the behavior and some of the constraints that make those arrays fast and relatively inflexible. If we weaken some of those constraints, we can actually add a lot of more flexible features and behavior into arrays, probably with some decrement in performance. Now, Python lists and Java arrays lists, which you might have used in your Java class, they get around some of the limitations of plain old ordinary arrays because they're somewhat more complex. And they have, of course, a bit slower performance, but they're much more flexible. Python list and Java array, I'm saying, are fudge ripple, meaning they're not just vanilla. They're actually have got a lot of features that make them very cool and interesting. Maybe you don't like that analogy, or maybe it makes you hungry. I don't know. Let's look at this sort of generalization in the next few slides. First of all, remember this model. This is the model of this simple array, the basic array. The numbers above the top are the indexes that are used for direct access to the array elements by index or by subscript. The numbers in the boxes are, fictional values that might be stored in those particular array locations. The dot, dot, dot means I didn't want to draw a whole bunch of extra boxes. And the numbers along the bottom are the simulated machine addresses, showing that if ints are actually 8 bytes wide, these would lie in successive addresses, starting, let's say, at 400. We're just stipulating that. Element 1 would be at 408, element 2 would be at 416, and element 19 would be at 560. So that's how, if you remember the discussion of address calculation, that's how that works. This array appears to have a size, sometimes called a length or an extent, depending on which language you're talking about, of 20. Now, access to an element is 01, so it doesn't depend in any way, shape, or form on the number of elements. Searching for an array, not so much. It is basically, I wrote O in by 2, but it's actually O in. So let's look at the next slide and see what a generalized array looks like. Here's a fancy or generalized array model. Looks a lot more complicated, but that's because it's got a lot more features. First of all, you can see it's still accessible by index. The 0, 1, 2, up to 19 still work. But now, instead of those index numbers taking you directly to the array element by address calculation, they take you to a pointer or a reference that actually points to the value, the real value. So there's a level of indirection here that's not present in ordinary arrays. But that level of indirection gains a lot of generality because now you can have, as you see in this picture, elements of different sizes. Now, the array indices are all exactly the same size, of course. They satisfy the constraint that they're stored contiguously, they're identically sized, they're accessed with integers. But when things they point to, or in the case of Java, refer to, are any kind of object that you want of any size. And of course, there's no guarantee and no promise and no need to think that the actual values of the arrays are stored contiguously anymore. They might be scattered around all over memory because we have in that row of indices a pointer to the actual location of the data. So we can actually mix and match types in this kind of array, which is much more flexible. It's still 01 to access an element because you can still use the index To go directly to it, you pay a slight overhead in actual performance to follow the indirection, but it's a minimal penalty. The implementation is such that in Python, we'll talk about Python and Java separately. Python as C-based code, right under the skin. So you don't have to drill down very far in the Python language to find that it's actually using compiled C code. It's one reason why Python is a very fast scripting language. I would argue faster than Java, but I'm sure some Java gurus or advocates out there will come back at me. But so essentially Python stores a C array of indices, and when you access a list, that's what it's called in Python. It's not called an array, it's called a list. And you're using the same structure to drop into the C code and find the actual element by pointer. Those of you who took the C class and either loved or loathed pointers, well, here they are in play. The link there tells you a lot more than I have about how Python's list is implemented. A Python list not only permits you to access elements by their index, which is still 01, but you can also access elements. You can append new elements, you can insert elements, you can delete elements. And those are, of course, much more complex operations. In Java, just about everything is a reference anyway. In other words, you're rarely dealing, except for the so-called atomic or primitive types like int, you're rarely dealing with the actual value itself. Usually you are dealing with a variable name, which is a reference to the actual values. So the arrays, the array of indexes that we see for the array, it just basically contains references to where the actual data is. If you define it, of course, in Java, you have to define it as an array of something. Python's loosely typed, and you don't have to do that. You can just kind of stick things in an array and of different types, and they'll work. However, in Java, you have to say. So in Java, you make it an array list of object. Now the world is open to you because everything in Java derives from object. So you can put different types in the array seamlessly. And the second reference shows how that actually works in terms of Java ArrayLists. Note that in both implementations, the array index is contiguous. So you can easily find the array pointer or reference that you want from the index with minimal calculation, but the data elements are usually stored somewhere else in memory, probably on the heap, which allows them to be different sizes and in different addresses. So you still get the quick access, but you have now a lot more flexibility, and you've paid a small performance penalty. As I said, access by index is still 01, but it will be a little slower due to the indirection that's required, but it's not bad. Searching for an element now, of course, in these structures is still ON on average. You still might have to search through every one of the every one of the indices and follow it to the pointed to data to see if the value you want is actually there. So that potentially that grows with the number of items and slows down the number of items. So that's ON. It's still a huge convenience and able to store heterogeneous types in your array. In fact, you can have an array that has other collections within it. So you have an array of arrays, or array list of array lists, or a list of lists in Python. And that's a very powerful data structure. And we'll actually be using some of that functionality in an upcoming project. Insertions and deletions are still problematic, worst case, since they still may entail moving a lot of data around to make up for